Welcome back. This is Mrs. Stipe again with our second video on doubling and half-life practice. All right, let's get started. The question says, if a substance has a half-life of 45.5 days, what is the daily decay factor? All right, when you see this, statement, you need to think immediately that the equation that's being modeled is that we have an initial substance. The B value is 0.5, meaning that 50% of it decays, and because it decays every 45.5 days, that is the equation that comes from that sentence. All right. To turn it into a daily decay factor, we want to simply look at the 0.5 to the T over 45.5, and we want to rewrite that so that the 0.5 is to the 1 over 45.5 and then to the T. Okay. We know that multiplication is commutative, and since we're multiplying T times 1 over 45.5, it doesn't matter the order we apply it. So we're going to put this into our calculator, and we get a base of 0.985 rounded to the thousandths. And so P of T equals P sub 0. And that is the equation that shows a daily decay factor as opposed to a half-life equation. So it's not only important that you can come up with the 0.985, but you understand what it is that we did. So let me try and explain this. This equation says that I start with a substance, and every time 45.5 days go by, the substance cuts in half. This is that same substance, but instead of having to wait 45.5 days, we use this and find that every day we have a decay factor of 0.985, which if we subtract that from 1, we get 0.015, or a 1.5% decay rate. There's my rate as a percent. Okay, so it's really important that you not only can do the procedure, but you understand what we're doing. Okay, so let's try this one. Now we have a half-life of 13.9 hours. So using the same procedure that we did in the problem before, we're going to make this T over 13.9. So we're just going to take the 0.5 out. First, we're going to take it to 1 over 13.9. and then to T. When we put 0.5 to the 1 over 13.9 in our calculators, we get 0.951, and that is the B, the daily decay factor. All right, so this is the half-life equation. Here is the same equation, not with a half-life, but with a daily decay, 951 to the T, daily decay factor. Wonder why that's there. Okay, let's go on and do some doubling questions and see how these are different. So if a population doubles every 8 years, then we immediately think that we have a function with an initial population. We multiply by 2 not every year, but every 8 years. Okay, so using the procedure we did in the upper two questions, we're going to take that 2 to the 1/8 to the T. And when we take 2 to the 1/8, we get 1.091 to the T. So this is our annual, okay, so this is a yearly one. This is an annual growth factor. So this equation written with an annual growth factor would be P of T equals P of 0 times 1.091 to the T. Okay, let's go ahead and do the last one. And this time, instead of using P0, we're going to go ahead and apply a money to it. So let's say I have $500. Not my money. I have $500, and it takes 15.75 years to double. And so I might want to know, but what's happening every year? All right, so here we go. We're going to say our function is that we start with 500 and we double every 15.75 years. Okay, so we're going to rewrite this, and we're going to take 2 to the 1 over 15.75, right? So 2 to the 1 over 15.75, we get a value of 1.045, and so the one on top, this is the doubling equation. This is the annual growth factor equation. But if you were to graph them, they would lay right on top of each other. Okay, I'm hoping that these 4 problems will help you to make sense of this section on doubling and half-life. See you in class.